So recording is on, so shall I start from this point?
Yes, sir.
Okay. Okay, so let us move to the slides now. Okay, so yesterday we have studied till this point that what was the energy and energy interaction. So energy, we studied that energy and what are its major constituents. We studied that it has microscopic and macroscopic constituents. So we also discussed that what are further components of these two. Okay, so let us now try to understand that what are the ways through which this energy can get transacted. Okay, so let us try to understand energy transactions. Okay, energy transactions. So what does it mean that, see, you know that there are ways of energy. So how do you transfer energy? Because the all the process, all the thing is concentrated through which that how do you transfer your energy? Okay. So there are three methods basically to transfer the energy. One is through work, one is through work, and second is through heat, and the third one is obviously mass. See what happens that if you provide some work to a system or you take out some work from the system, so what are you trying to do is you are trying to put some energy in or you are trying to put some energy out of the system. So this is the way how you can interact with the system. So work is one of the ways, so I will rather write work interaction. Okay, and the second thing is heat interaction, and same thing, like how do you transfer your energy, like we have seen various examples. How do you means how do you go to energy interaction, that you will provide some heat to the system and this heat will later on get converted into the work and then you are getting work as output. So what we can see here as like the heat is given to the system and work is coming out of the system. So these are nothing but the energy interaction. You gave some form of energy and you are taking out some another form of energy, right? So these two are ways. And the third one is mass interaction. What does it mean? Mass interaction. In mass interaction, what happens is that, see, let us say that 5 kilo 5 kg of gas is there. Okay, and now I am putting this gas into a container which was originally having some gas into it. So once this gas will come into picture, that once this gas comes into this container, let us say there is some container and some gas is coming in, then what will happen that this gas will carry some, let us say, some heat with it, some energy with it. So what we can see is that this is nothing but the way of energy interaction, that if you are pouring some mass with it, then the mass which energy it is already possessing, it will carry it to the required system. Okay, so we can see that energy can be interacted in what ways, that there can be work, heat, and mass interactions. This is why what that this was my motive to tell you that the what are the methods of energy interaction. Let us do quickly one example based on that energy interaction. Okay, see, let us say that there is a rigid container. See, whenever in thermodynamics somebody tells you it's a rigid container, that means that its boundaries are very rigid to move, like that whatever happens into the system, its boundary would never move. That means it automatically becomes what, constant volume container. And if this is insulated also, then there will be no heat interaction as well. If it is insulated, then there will be no heat interaction, and if it is rigid, then there will be no volumetric change. Let us say that there was a rigid container and it was insulated as well. So it is rigid and insulated as well. Okay. Let us say there is one chemical mixture into it and which can get what ignited, means if you ignite it, then it can get ignited and it can start burning. Let us say that there was one nozzle through which you, or not nozzle, this is an spark plug through which you provided some spark into this chemical and this started burning. Okay, then what happens, that your question will be that tell me what is the change in energy, what is delta E. So most of us will be thinking that, sir, if this is spark, then this will start burning and its temperature will change, that means its energy will increase. No, this is wrong. Why its energy will not be increasing? Because see, energy, we have seen that energy is a constant term. It can never it can never be created or nor be destroyed, only it can change its form. So what happens here is that once you sparked this one now, then what happened, that there was forms of energy. Let us say that there was sensible part of it, there was latent part of it, and then there was chemical part of it, and then there was nuclear, right? So let us not worried about this nuclear now. So what happened here, once you provided some spark, the chemical energy which was stored into that gas substance has got converted into what? Sensible part. So can we see that this is the interaction within same energy? So energy anyway remained constant only, right? So the energy would not increase, rather I can say that yes, temperature will definitely increase, but I cannot say that energy is being increased. Okay, because I am counting upon all these three, that there was chemical energy hidden within it, that chemical energy has not now got converted into sensible part, then I cannot say that this has got convert means that its energy will also increase. Okay, this is what I was trying to say. Next. Now let us try to understand. See, we have seen now that there are ways to interact energy, work, heat and mass. So let us talk about these one by one. So first thing I am going to write down here is work interaction. Okay. So how do you see, or when do you say that like there is any energy interaction, right? Then how do you differentiate it between if it is heat transfer, it is work transfer or mass transfer? So work transfer is said when you can say that there is work interaction, when 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 the entire effect of the system, see, listen to me carefully, I'm writing down here, if the entire, this is very important to understand but not that important definitions, not means if the entire effect of the system, effect of the system on the surrounding, I will explain what is this, on the surrounding, on the surrounding can be converted into, can be converted into, converted into raising the weight. See, let us understand, we must have seen this definition, but we might not be able to understand what does it mean physically. Although weight may not be raised, See, let us understand what does it mean. See, when you will say there is any work interaction, let us say that you have any system, okay? And then if you try to, let us say that there is any system, any kind of system, okay? And then you need to identify if this is work interaction. Then what you will do, that you will get this work into what, raising of some weight. So how do you do that? That let us say that uh, there was a system, okay, and and I can see that if there is some output from this one, and if this output will help you to raise some weight, or it will, at least it will try. See, if it is not able to do, I don't mind that it is not able to give you that much amount that it can raise the weight, but it at least it should try to raise that weight. Getting the idea? Then I would say that okay, this is the work interaction. That means that I hope you understand that what is work interaction. This is nothing but, like, let us say that there is any system which is generating, or which you are not able to judge that whether this is work interaction or heat interaction. Then what you will do, that if you will try to convert, or you will try to watch out the effect of it on the surrounding. Then what you will do, that you will try to find out that if this given energy interaction can raise some weight, then you would say that okay, yes, this is energy interaction. Let us say there is some mass hanging on it. And then if this is not a, at least not trying to do this, then you would say that simply this is not the work interaction. This is as simple as that. And let us not get much complicated part into it. Like, just you should understand that if you are able to, if at least you can convert, or you can, through some mechanism, if you are able to watch that your energy interaction can help you to raise your weight. Okay, so now let us try to understand work interaction for what, fixed mass or control, what control, fixed mass or control mass we have seen na? So fixed mass system will apply fixed mass system. Like what we will do, that how to find out work interaction for fixed mass system, or we name it also that closed system. We have seen yesterday, right? Closed system. So what happens is that we know that work is nothing but force into displacement, right? And force is nothing but pressure into area. So can I write down that work done is nothing but force, this part is force, and this is displacement, right? So in thermodynamics, we are always having some pressure with us, right? Like if there is if we are working on atmospheric pressure, then we need to have higher volume so that we can produce some change. So what is the another possible thing is that let us change the pressure. That means we will be always dealing with pressure. So the pressure thing, we will be all being counting upon it. Like we will not be able to find out directly pressure. We know, sorry, force. We always know pressure. So that is why we are trying to get it converted into the terms of pressure. Okay. So can I write down the work done is nothing but the force into displacement. So if you think one step further, can you think that this pressure is here only, but can you think that this A into dx is nothing but the change into volume dV? So can I write down that this is nothing but del W is nothing but pressure into what? Change in volume. But this is strictly applicable for whom? For closed system only. Okay. Mind the word, you cannot apply this formula directly to the open systems. You can always use this formula for the closed system, but you will never use this formula directly for the open system. Okay, so now, and why I have used this integration sign, like if there is some variation of pressure with the change in volume, then I will have to integrate it between the volumetric limits. So V1 to V2, I will have to integrate it, right? So then I can write down that this W is, this dW is nothing but W. So this is nothing but integration of PdV with respect to volume, and if you know the limits. Okay. Second thing, where you will be applying this is fixed, always fixed. That one thing is that you should be given with closed system. If the question says that this is not closed system or anything they are willing to attain, then you won't apply this equation directly. And second thing is that we have indirectly assumed that is it is quasi static process or reversible process. Why? Why I'm telling you that this is reversible or quasi static? Because if this is not reversible or quasi static, then I don't know what possible path it has taken, right? So in order to know the path, we should know that the process is reversible, otherwise I'm not able to determine the path. So why I'm telling you this, this walk is integration pdv. This we have seen now. If we try to plot it on pressure and volume axis, pressure and volume axis, then can you see that if I plot it here, like let us say that this was the variation of pressure and volume, then can I see one thing, that this is nothing but the area of this curve on the volumetric axis, right? And in fact this is that dv, right? This is that dv which we have seen. So can you see that unless you know this path, let me change the color of this one, that unless you know this path, this blue one, then you are not able to find out the area now. Like if you know this path, then only you can find out this area, otherwise how you will determine this area? That means this path is always fixed. So if you know this path, then only you will integrate it. And when we know this path, when the process is what? Reversible or quasi static. Okay, so I hope you appreciate that why we have studied these things earlier. So reversible or quasi static, this is mandatory that it is reversible or quasi static. Then only I know this path, then only I can find the area of this curve on which? On volumetric axis. Okay. Second thing, that walk is not a point function, but rather it is path function. Let us appreciate it how. Let us say that you are reaching from point 1 to point 2. So what does point 1 and point 2 means? That this is pressure and volume axis. So here we have P1, V1, and here we have another P2, V2, right? So if you are reaching P1 to P2 V2, like P1 V1 to P2 V2 through this path, let us name it as A. And there are another ways of reaching it. Let us say that I have taken some alternate path like this one, and this is named as B. So can you see that when you go on finding the area or work done, what you will do, that you will find out the area of this curve on the volumetric axis. So can you see that the area of the curve 1a2, this is not equal to area of the curve 1b2? Why? Because this is the area which b part, like 1b2 will be having more compared to 1a2. That means that what, the work is not path function, point function, rather it is path function. Why? Because it has started depending upon the path which you have followed for reaching from the point 1 to point 2. So we'll name it as what? Work is path function. So the questions from this area also keeps on appearing. So can I write down few important points about work? First, very important is that I have already told you, I need not to write that area under the curve on the PV axis, on the PV diagram, area on the curve on the volumetric axis gives you the magnitude of work done. First thing. Second thing is that work is path function. We appreciated this fact. Third is that work is an inexact differential. You cannot write down this one directly, that this del W is del delta W is W2 minus W1. This you can never write, okay? Why? Because this is following upon the path now, so you cannot find it exact differential. And second thing is that okay, second thing about it is work is a boundary phenomenon. Let us understand how work is boundary phenomenon. Like if boundaries will not move now, then there will be no work. And we can see, I'm strictly again talking about whom? I'm talking about closed system. See, if there is no movement in the boundary, let us say that there is no movement in the boundary. Let us try to analyze this example of piston cylinder. See, if I have created this virtual boundary here, like I have defined that this is the system, then can you see that unless this boundary gets changed, your volume will not get changed. That means that if this boundary moves, then only I can see that there can be work interaction. If this boundary is fixed, there cannot be work interaction. Why? Because I have appreciated this fact that work is what? PdV, that means dV is the change in volume. If this system boundary remains fixed, then how there will be change in volume? If there is no change in volume, there is no work. So that is why it is says that work is boundary phenomenon, right? Next thing. It says that work is a transient phenomenon. That means work is defined at two time instants. Like what I will do is that is let us say that I have started something started at point 1 and I have reached point 2. So this cannot happen without expanding the time. That means that I am transient. Like with the expense of time, my work will come into picture. So whenever there is some work interactions, that means it is transient, like it is defined at two time instants, right? Then only we find the rate now in, like let us say that you know kilojoule, then you try to find out kilojoule per second. So you are trying to find out that what is that time which you have taken. So this is why we say that work is transient phenomenon, because unless the time has spent, I cannot say that the work will be done. Why? Because there is some time required. Let us say that if this boundary has started movement, that means it has happened at two time instant. Let us say that if you have started your journey here and have reached till this point, then this has to be transient. Otherwise, how this is possible that within no time instant this will reach from this point to this one? That means it is a transient phenomenon. Okay, next. And work depends upon past history, and anyway it has to. Work depends upon past history. What does it mean? Work depends upon past history. See, let us say you are integrating PDV, okay? And you know that there's some pressure and volume relation. If you know, like if you know pressure in the function of volume, if you know this fact. See, if let us say that I am having a temperature 10 degrees Celsius, then let us say that the same system is at 100 degrees Celsius, and if the same system is at 1000 degrees Celsius, then every time your requirement from, let us say that you are having a delta T of 100 degrees Celsius, and here also you are trying to reach to 200, then delta T is anyway 100, and here also your delta T is 100. Then it will never happen that your work requirement in all these three will be same. That means that work is now dependent upon what? That what was your initial condition then only it will tell you that what is del W required to reach from system 1 to, or let us say state 1 to state 2. So we appreciate this fact that what, that work is dependent upon past history. That means that how or what was your initial state, and anyway if we have fixed the final state, then your work requirement will be dependent upon that what was your initial state. Got the idea? So these are the important points about the work. Let us now move to let us try to find out this work done, the magnitude of this work done for certain process. Okay, see how any process can occur in nature. So there are 5 process in which we have seen that most of the process following any one of these. Okay, so let us try to find out now non-flow work. Non-flow work means what? This is nothing but closed system work. Okay. So let us first go through constant volume. Constant volume. See, what does it mean if I say constant volume? Again, this is the example of rigid container only, or if you are using piston cylinder assembly, then you are having stoppers, like piston is fixed between 2 stoppers, something like this. And if the piston is fixed in this area, then only I can say that this will be working upon constant volume, that piston is not able to move upwards and downwards. Then they will ask you that what is the, if you supply some heat, then they will ask you that what is the work I am going to get. Then if you are smart enough, there is no boundary movement, that means the volume is constant. If there is no boundary movement, volume is constant, the work done will be directly 0. Why? Because W is integration P dV, and just now you have told me, sir, that dV is 0. Why? Because volume is constant. Okay, and this is also named as, constant volume is also named as isochoric, or this is also named as isometric. Next. Next is constant pressure. Constant pressure process. Then see what questions appear in exam, that they will tell you that there is a change in state from 1 to 2 and the pressure is constant. They will give you the change in volume and they will ask you that tell me what is the magnitude of work required. When you will be solving problems now, then we will see that how the questions appear in the exam. Okay, constant pressure is also called isobaric, and it is also called isopistic. Okay, so what happens in constant pressure process, what you will do, that W is integration PdV. Okay, and if pressure is constant, you can take it out of the integration, right? So you can directly write down it is PdV, and dV itself will be what? P into V2 minus V1. Like if I integrate it between V1 to V2, then can I write down that for constant pressure, work done is P into V2 minus V1? I can write, yeah. Then let us move to which one? Isothermal process. See, constant pressure means what? That there, if you applied some heat or you take some work from that system, but the pressure is not going to change. Okay, then we name it simply constant pressure process. And then there is isothermal process. Isothermal process, then it simply means what? That temperature is constant into this one. Temperature is constant. Then now if you will go to find out the work, what you will do, that again W is integration PdV. Now you need to find out that what is the pressure in terms of volume, right? If you know this one, then you will put into this integration, and then you will find out, integrate it between the work V1 to V2, and then you will be able to find out the magnitude of work interaction. Simple. But mm, every time you will not be aware that what is this function. Let us say that they will tell you that this is an case of ideal gas. So this is applied for whom? Like if you know this pressure in terms of volume, then you can apply it for anyone. But if they will mention you that this is an ideal gas, then we already know that what is the relationship between what? Pressure, volume and temperature. So if it is an ideal gas, then what we will do, that we know this equation that PV is MRT, then what happens, that we know that mass is constant thing, right? And this R is what? Characteristic gas constant. This is also fixed once your gas is fixed. And then there is third term, temperature, and temperature you have fixed here, right? So can you see that this whole term has got converted into some constant? I am strictly talking about whom? Ideal gas. Okay, so if I have find out that okay, the PV is constant, then I will go to find out what is the magnitude of work interaction. W is integration PdV, and I have seen that PV is equal to constant. So can I write down P as nothing but C upon V? So this is C upon V dV. If you integrate it, this is C into log of V2 upon V1. Can I write down this one? Yeah. And what about C? What is C? C is nothing but P1 V1, and this is equal to P2 and V2 also. So if sometimes they will only mention you one of the pressure and either of the like volume. So how you will find out that if in this one in terms of pressure, that you will do is that V2 upon V1, here we can see that V2 upon V1 is P1 upon P2, so we can write down this one as P1 upon P2 also. Okay, sometimes directly they are asking uh, constant uh, temperature process work done by if there is the substance called ideal gas. Okay. Next, let us move to this one very important equation, adiabatic process. For adiabatic process, this Q is always zero, means there will be no heat interaction. Whenever I say that there is a adiabatic process, then you will automatically assume that there will be no interaction of heat. There can be work or other interaction, but there will be no heat interaction. It will be insulated, so there will be no heat coming into the system and no heat will be going out of the system. And then you will integrate again what? W is integration dV. Okay, but again if you are having this ideal gas, then in adiabatic process your variation of pressure with respect to volume is something like this. We write down PV to the power gamma is equal to constant. Then if you put this one into the integration, then can you write down that this is nothing but C upon pressure is nothing but C upon V to the power gamma, right? So I'm writing down this one, C upon V to the power gamma into dV. Okay. Then when we integrate it between V1 to V2, then can I write down this one as W is equal to C into V, this is V1 and this is V2. So can I write down this one as V2 to the power gamma minus gamma plus 1. See, you just do one thing, that you take it on the what? Numerator. So this becomes V to the power minus gamma. So I have just taken that one on the upper side. And then now the integration is simple. This is nothing but minus gamma plus 1. And if you put the lower limit, this will become V1 to the power minus gamma plus 1 divided by minus of gamma plus 1. Okay. And then you what? You take this C into this one, and C is nothing but P1 V1 to the power gamma, and this is equal to P2 V2 to the power gamma. And then if you take this C into this one, then can I write down that this is nothing but P2 V2 to the power gamma into V2 to the power minus gamma plus 1 minus of P1 V1. Why? Because C is equal to P1 V1 also now. So I can write down. So P1 V1 to the power gamma into V1 to the power minus gamma plus 1 upon minus gamma plus 1. So now your work done is nothing but what? This is P2 and this becomes B2. Why? Because minus gamma and plus gamma, this will be what? 0 only. So can I write down this one as V2 minus of P1 V1 upon minus gamma plus 1, or we can also write down this one as P1 V1 minus P2 V2 upon gamma minus 1. So this is the magnitude of work interaction when you are talking about adiabatic process, and this is valid for whom? When you are what? You are working with ideal gas. We should never forget that when we derive this equation now, then what were the assumptions? If you forget the assumption, and then you will apply this same equation to the wrong scenarios also, but which will be absolutely wrong, right? So whenever we are applying these equations, we should know that what was the assumptions, right? And then we have seen four processes, right? And then the fifth one is polytropic. This is nothing but the what variation of something like above. What do we do here is that pressure into volume to the power n is equal to constant. So here what do we do that this is nothing but any general process, and n can vary between what? Generally n is varying between 1 and gamma. Okay, although it can take any other values also, but generally for our practical devices this is varying 1 to gamma. So the work done will be nothing but the same like adiabatic, but why? Because the nature of variation is same. Only if I write down this one for polytropic, then I can write down W is P1 V1 minus P2 V2 upon n minus 1. Instead of gamma, the variation was with n. So I have written down here, instead of gamma, I have written n. This is the only difference in terms of means, in terms of derivations. Okay. Now, now let us quickly try to understand ideal gas. Why? Because we will be mostly dealing with this one. So let us try to understand what is ideal gas. Okay. Ideal gas. So whenever you are assuming any gas to be ideal one, okay, then you are automatically assuming following things. Let us see what are those. One thing which we are assuming in ideal gas, what I am writing down here is assumptions. Okay. One very important assumption is intermolecular forces are negligible. What does it mean intermolecular forces are negligible? See, let us say that there is some container and there is some gas into it. Then I am not worried about that what is the intermolecular force, but I am only worried about that what they are putting as a whole. Right, like I am worried about the substance as a whole, but I am not worried about that what is their intermolecular forces, right? And the second thing is that volume occupied by volume occupied by gas molecules will be negligible, should be negligible compared to the container volume, okay, compared to the container volume. See, what does it mean? See, if you are talking about any container and there is some gas into it, then what do you say that what is the volume of this gas? The volume of the container. But there are molecules also which have occupied that container. So we are not worried about that what volume these gas molecules have occupied. What we generally do is that we neglect the volume of gas molecules. And then what is the favorable conditions for applying ideal gas? These are the assumptions. Like whenever you say that there is some ideal gas, then these assumptions are automatically into picture. And then there is one thing called favorable condition, like when situations will be favoring that you can assume that the given gas is ideal gas. So I'm writing down what are those favorable conditions. And what are the favorable conditions? One is your substance, like the place where you are dealing with it or the container where you are dealing with it. Then mostly what it is that you are dealing with low pressure, you are dealing with low pressure and and high temperature. Okay. So whenever there is this condition satisfied, there is low pressure and high temperature, then we can easily assume that the given gas is ideal gas. And what is this low pressure and high temperature? What is this magnitude? This is compared to the what? Compared to critical point what? Compared to critical point pressure and temperature. So compared to whom? Compared to point critical point pressure and temperature. Okay, see, then there are few conditions where you should directly assume that it is ideal gas. Like most of the gases, like substances which are existing as gases in general, then we will assume those as ideal gas. So gases normally will be considered as what? Ideal gases. Gases, you can consider those as ideal gases. For example, let us say that they are talking about oxygen, they are talking about nitrogen, they are talking about air, they are talking about carbon dioxide. Then you can simply say that this, we can say it's an ideal gas. Okay. And then there is next condition, that water vapor, we'll be dealing with water vapor. So to some, like to some certainty, to some error, we what do, that we assume that okay, the vapor is also ideal gas. But if they mention that you considered it as ideal gas, then only you take it as ideal gas. Otherwise you should not take it as ideal gas, depends upon the scenario. But steam is never taken as ideal gas. Steam is never. Steam means what? The wet phase, like where liquid and vapor phase are coexisting, then you will never assume that it is what? Ideal gas. So steam is never considered as what? Ideal gas. Okay. If they mention you that okay, assume ideal gas, then you can anyway assume. But if they are not assuming, then you should also not assume. This is my concern. Okay. See, let us now try to move to what are those ideal gas equations. So we must have seen two equations. One is PV is equal to MRT, and one equation we have seen that PB is equal to N into R bar T. So what are these? This is pressure and volume, this we know. So what is this M here? M is nothing but mass, and R is characteristic gas constant. What do we name it? Characteristic gas constant. And T is nothing but absolute temperature. And here we need to take care. Like this, we are aware on anyway. Now let us try to understand what are these variables into this equation. See here your N is, I am writing like this. Here your N is number of moles. Okay. And the unit possibly will be what? Kilomoles. Okay. And here your R bar is called universal gas constant. And what is the unit of R bar? The unit of R bar, this value is fixed. The R bar value is fixed. This is 8.314. The unit is important. This is kilojoule per kg mole Kelvin or kilomole Kelvin. Kilojoule per kilomole Kelvin. Okay. Then let us say that they will say you 1 mole of O2. So what I can say that 1 mole of O2 is having how much weight? 32 grams, right? Then they will ask you that what is the weight of 1 kilomole of O2. So 1 kilomole of O2 will weight how much? 32 kilogram. Okay. So this is how you convert units. Okay. So 1 kilomole or kg mole, these two are same thing. Let us not confuse with this one. 1 kilomole and kg mole are same things, right? So unit of R bar we have seen here. Okay. So if you are putting these variables in this equation, then you should take proper care of the units. Otherwise, you will be committing some mistake. Okay. Now let us come to this one. What is R? R is nothing but this R bar we have seen now, which is divided by molecular mass, right? So R bar is R bar upon M. Here your M is molecular weight. Okay. So this you should take care that how to find out R which is characteristic gas constant if you know R bar, and then they will tell you that what is the, let us say, oxygen. Then they will, let us say that they ask you that find me the R value of O2. Then how you will find out the R bar we know. The R bar value I know that this is 8.314 kilojoule per kilomole Kelvin. Okay, this I know. And then I know the molecular weight of 1 mole of O2. This is 32 gram. Or can I write down this is nothing but 32 kg per kilomole? Yeah, from this one I can write down now that this is 32 kg, and for how much? 1 kilomole. So I can write it down like this one. So this kilomole and kilomoles will get cancelled out. So can I see that the unit of R becomes kilojoule per kg Kelvin? So with the help of units also, you can identify that what value they have given to you. Okay. So let's not be worried about this one also. Okay. Now let us apply this ideal gas equation for various process. So I am writing down next is ideal gas equations. Ideal gas equations for various process. So how to do this? Again, we know this part, this PV is equal to MRT. So this we will always keep in mind. So let us say that I am applying it to constant pressure process. Constant pressure process. See, one thing, this PV is equal to MRT. From this one, I can deduce one thing. See what? This M into R, the product of M into R will be always constant. Why? Because I am dealing with what? The mass is not getting changed here. So, can I see that I can write down P1 V1 upon T1. Why? Because M into R, the product is constant. So can I write down P1 V1 upon T1? This will be equal to P2 V2 upon T2, and this will be nothing but equal to MR. Suppose you were at state 1 and you reach the state 2, then it says that this ratio P1 V1 upon T1 will be equal to P2 V2 upon T2. So here we know that we are dealing with constant pressure process. That means P1 will be equal to P2. So for constant pressure process, can I write down that V1 upon T1 will be equal to V2 upon T2? Fine. Same thing we will do with whom? Constant volume process. Constant volume process. So for constant volume process, again, we know that P1 V1 upon T1 is P2 V2 upon T2. So let me first write this equation every time. So can I write down P1 V1 upon T1 is P2 V2 upon T2, and then it has been mentioned that this is a constant volume process. So this V1 and V2 gets cancelled out. So can I write down this one as P1 upon T1 is equal to P2 upon T2. See, why we are studying these things is that most of the time we are dealing with ideal gas. They will tell you, they will ask you that there is some container, it is going, let us say, constant pressure process, constant volume process. Then they will give you some variables directly, and then they will ask you about the other ones. Okay. Okay, fine. So next thing is constant temperature process. So same thing you can apply on constant temperature process also. Constant temperature process. In this again, what we will do, the same equation. So I avoid here, your temperature terms will get cancelled out. So I'm directly writing down this one as P1 V1 is equal to P2 V2. This we have seen earlier also, just now when we were dealing with isothermal process. So this I am strictly, see, don't forget that unless they will tell you that this is an ideal gas, you cannot apply this equation. And where these things will be helpful, let us say that they will tell you that there is a rigid container, you applied some heat into it, the pressure is changed from P1 to P2 and the initial temperature is also given to, they will ask you that what is the final temperature. Then if you know that how to apply this ideal gas equation for constant volume process, then you will be directly able to reduce yourself to this equation, and then you will find out. Okay, next. And next two process, very important and very important, I would rather say, that every time the relationship itself or the applications of it multiple number of times, we have seen the questions appearing from this area, that is adiabatic process. Okay. See what happens in adiabatic process. We know that this is PV के power gamma is constant. PV to the power gamma is constant. This we know. Now, if we apply this one, the same one for ideal gas, then what happens that, can I write down the ideal gas equation again, that PV is equal to PV upon T is equal to constant. Why? Because PV upon T is MR and this is anyway constant. And we have another variation is strictly for adiabatic process. You cannot apply this one to any other. So using this one, can I see that V, this from this one, V is directly proportional to whom? T upon P. So we can see V is directly proportional to T upon P. So then you will write down that P is T upon P to the power gamma is equal to constant. So can I write down from this one, can I write down that T to the power gamma, if you apply this to two given states, so can I write down, or let us make it generalized term, that this is T to the power gamma and this is divided by what? This is P to the power gamma on the denominator and 1. So can I write down this one as P to the power gamma minus 1? So can I write down this is constant? Then if I apply to the two given conditions, so can I write down this one as T2 upon T1 to the power T2 upon T1, or in fact, can I write down this is P2 upon P1? This gamma minus 1 was already upon, this is 1 upon gamma minus 1. So this is gamma minus 1 upon gamma. Okay. See, if you open this one, then this is nothing but P upon P to the power gamma into T to the power gamma. So when you make it open further, then can you write down this is T upon gamma upon P to the power 1 minus gamma. 1 minus gamma, and if I take it in denominator, then I can write down this one as T to the power gamma upon P to the power gamma minus 1. Okay, so this is what I have used. Okay, fine. So this T2 upon T1 is P2 upon P1 gamma minus 1 upon gamma. Okay. No, this is pk power gamma minus 1 only. This is not like 1 upon. Okay. So this is 1. Why? Because let us apply T1 to the power gamma, 1 to the power gamma minus 1 is equal to T2 to the power gamma is equal to P2 to the power gamma minus 1. So can I write down this one as T2 upon T1 is equal to P2 upon P1, and here we have already gamma minus 1 and here we have gamma. So you take this gamma on this side, so this becomes gamma minus 1 upon gamma. This I have directly written here. Okay, so let us understand this. Similarly, when you will go to polytropic process, when you will go to polytropic process, the variation is PV to the power n is constant. So here what you can see is that I will directly write down this ideal gas equation. Why? Because we have already reduced it for adiabatic process. So we can already only change this index, right? So can I write down here that T2 upon T1 is nothing but P2 upon P1 to the power n minus 1 upon n. So this is valid for whom? Polytropic process. And the volumetric relation obviously will become T1 V1 to the power n minus 1 is equal to T2 V2 to the power n minus 1. Okay. Now, very important part is representation of ideal gas. See, how do you draw these process? Like we have seen constant pressure process, constant volume process. We have seen adiabatic, we have seen isothermal and polytropic. So how do you plot these process on this what PB chart? So if it is a constant pressure, what it will be? It will be a horizontal line, right? Like any horizontal line, this will show you constant pressure. And what about constant volume? A vertical line. A vertical line will be what? Constant volume process. These two are easier to draw, but the problem occurs with whom? One is adiabatic process and another one is isothermal process. We know that PV to the power PV is equal to constant for isothermal, and we also know that PV to the power gamma is constant for adiabatic process. Then the question arises that how do you plot these two? So this is this PV to the PV is constant. This is nothing but the equation of rectangular hyperbola, right? So how do we draw it? Like if I can find the relation between these two, and if I can draw this, I can draw this one also. So let us first try to find the slope of this curve. PB is equal to C. So PB is equal to C. If I write down PB is equal to C, if I take the differential of this one, then can I write down VDP plus PDV is equal to 0. So the slope of this curve dp upon dv, dp upon dv, can I write down this one as minus of p upon v? Yes, I can. And let us go for polytropic process or adiabatic process. So this is PV to the power gamma is equal to constant. So if you differentiate it or take differential of this one, then can I write down P into gamma times V to the power gamma minus 1 into dV is equal to, or let us take it on one side first. This is V to the power gamma into dP is equal to again 0. So can I write down from this one dP upon dV is, here what we can see is that uh, we can cancel out V to the power gamma from both of the terms. So this will be, this is gamma only. So this will be turned out as what? Minus of gamma times P upon V. See, the relationship between these two is established now, more established, right? Like if I know the slope of what? Constant temperature process, then I can find out the slope of what? Adiabatic process, which is gamma times the slope of isothermal process. And if I can draw this curve, then I can automatically draw this curve also, right? Let us say that if you are drawing a curve, like say if you see that this is an isothermal curve, then then the adiabatic curve will be what? Gamma times of this one. Yeah, simple. And let us say that you are expansion, this is the case of expansion. So this is your adiabatic process and this is for isothermal. This is isothermal and this is adiabatic, right? And let us say when you are compressing it, and then if this is isothermal, then what will be about adiabatic will be again gamma times of this one, right? So this will be showing you adiabatic process. Okay. So adiabatic process will be always steeper, right? So now we know how to represent it on the PV axis. Yeah. Like PV to the power, this is pressure is equal to constant. This is volume is equal to constant process. And then we have what? Isothermal process. And then we have adiabatic process. And then we have polytropic process. And this polytropic process would lie into this one. So can I see that this is constant pressure process, this is constant volume, this is isothermal, this is for polytropic, and this is for adiabatic, right? See. Now, like we have seen this PV to the power n is equal to constant. So based on this value n, we can generalize any given process as polytropic one. Let us see how. Let us say you are dealing with constant pressure process. So how you can achieve constant pressure process? You know that this P1 V1 is equal to P1 V1 to the power n is equal to P2 V2 to the power n. Why I am writing like this? Why? Because I am trying to find out that what value of this index n I put so that this process becomes what? Isothermal. So see, can you see that if I put this value n as 1, then I can achieve that this sorry, this if this n is 0, if this n is 0, if this n is also 0, then can you see that this P1 is equal to P2? Yeah. So can I see that the constant pressure process is also an polytropic process where the index is nothing but 0. So can I write down this one as 0? When you go to isothermal, then what did you find? That P1 V1 was P2 V2, right? And here you are trying to find out this relationship through PV to the power n. So can you see that P1 V1 to the power n, it should be equal to P2 V2 to the power n, and anyway this should reduce back to this one. Then this is only possible when this n value is equal to 1. When this n is equal to 1, then only I can write down this P1 V1 is equal to P2 V2, right? Okay. Similarly, for polytropic, we know, for adiabatic, we know, and for volumetric, this n becomes what? Infinity. So you have started from 0 and your n value is increasing in this direction. Sometimes they do ask, but not that important. But sometimes they might ask you that what is this index of this polytropic index for isothermal, adiabatic, or anyone, you should be able to answer. See, now we are done with work transfer for closed system. Now let us move to whom? Let us move to heat interaction. Like work interaction we have already seen. So let us move to heat interaction. See, how do we say that that any energy interaction is heat interaction. Heat is the energy interaction when it is having by the virtue of whom? By the virtue of temperature difference. By the virtue of what? Temperature difference. Okay. So how you will find out heat interaction? See, let us say that there is a system. Okay. Like there is any container and then it is having a coil within it. Let us say this is an heating coil. So let us say that your system is something like this one. Like you are defining your system boundary in such a manner that this electric heater is not the part of this system. Then from this point to this point, how your energy has traveled. The energy must have traveled due to temperature difference. Then we can say that this is heat interaction. Why? Because this was not the part of the system. Then there must be, if this is system, and this is not the part of system, this rather becomes surrounding. If this becomes surrounding, then there is one interaction between system and surrounding. This is due to whom? Due to temperature difference. If the temperature of this heater is higher to the system, then there will be energy flowing from this heater to the system. Then we name it as heat interaction. Why? Because this is happening due to what? Due to temperature difference. Let us consider the same system again. Let us consider the same system again. Okay. And now what I do is that I take this heater also into my system. If I take this heater also into my system, then this is what kind of heat transfer? See, your energy is being transferred to the system from some part, but is it due to any temperature difference? No. Why? Because this is the part of system only. This heater is part of system only. Then here your energy interaction is nothing but work. Here your system was like this heater was not the part of system. Then here the energy interaction was heat. But here, since this heater is the part of what? This system, then I would say that this is work interaction. Why? Because there is no in a interaction due to what? Temperature difference. I hope you have appreciated this fact. Okay. Let us move to the next. Then how to quantify heat? Like we have quantified the work, like we have seen that work was integral PdV. Then how to find out the heat interaction? See, how do you find out heat interaction? Then can you see that, let us say, for example, you are hitting 10 kg of mass, 10 kg of mass, and then you are hitting 100 kg of mass. Okay, here you have 10 kg and here you have 100 kg. So can you feel that when you will be hitting 10 kg mass and again when you are hitting 100 kg mass, here you will require more heat compared to the previous one. Let us say that you are trying to achieve from 10 to, let us say, 15 degrees Celsius. Here also it was initially at 10 degrees Celsius and final at 15 degrees Celsius. So can you see that in order to achieve the same temperature difference, if the mass is more, you can feel it that you will have to apply more heat. So can I say that heat transfer is nothing but directly proportional to the mass of the system? One thing. And second thing, see, this is not heat transfer, heat interaction. Heat transfer and heat interaction are two separate things. Okay. Then can I feel that again, if I am taking same mass, let us say that I am having 10 kg, then in one scenario I am willing to achieve 10 to 15 and in second scenario I am willing to achieve 10 to 50. So here your delta T is 40 and here your delta T is 5. Then you will automatically feel that here your Q value will be lesser compared to this one. Then again can I write down that Q value is directly proportional to what is the temperature change you are willing to achieve. Then can I write down this one as Q is nothing but MC delta T. See, M and delta T we know, and this is C is the what? Proportionality constant we have introduced, and this is named as specific heat. Specific heat, and the product M into C is called heat capacity. M into C is called heat capacity of system, and C is particularly specific heat. Then specific heat is further divided into two parts. One is specific heat at constant pressure and one is specific heat at constant volume. Let us quickly analyze these two. See, you have one, let us say, piston cylinder assembly where your volume is fixed, means you cannot achieve any volumetric change. So your volume is fixed, okay? And you have another system where your volume is not fixed. You can expand or contract, okay? And you are applying same heat to both of these, okay? Then can you feel that if there is no volumetric change, this piston is not able to move? But here what you can see that this piston is not restricted to move, this is free to move. Then if you are supplying some heat, then it will what, acquire another position, it will reach to another position. So can you see that this way it has done some work also? Yeah, some work is also done, but here there was no work. We have seen this earlier, right? So here we have no work, but here some work is done. So can we feel that reaching from this point to this point, you have applied some heat, then that some amount of heat is converted into work. Yes, and you must be willing to achieve some delta T. So what happens that you will have to apply this work component also with this heat, then only you will be achieved to this delta T. That means compared to this one, you will be supplying more heat when you are dealing with constant what? This is constant pressure process. Then when you are dealing with constant pressure process, you have one component, what, work component, but here you have no work component. That means here some of your heat will get converted into work done. That means your delta T for the same heat will be not more. Then you will have to apply more amount of heat so that you are able to achieve that required delta T. So I can feel this fact again, that in order to supply or in order to achieve same delta T in the process when volume is constant and in the process when pressure is constant, you will have to apply more heat here and less heat here. So this specific heat value Cp is termed as specific heat at constant pressure. Specific heat at constant pressure, and Cv is termed as specific heat at constant volume. So with this explanation, I believe that you must have understood that Cp value will be greater than Cv. Why? Because Cp is also accounting what, boundary work within it. If it is accounting boundary work within it, then I must supply that amount of heat, then only this will happen. Okay, now thus the ratio of Cp upon Cv is called gamma, Cp upon Cv is called gamma, or ratio of specific heats. So this is gamma. Now let us understand the variation of Cp and Cv for various gases. So let us first talk about non-monoatomic gases. Non-monoatomic gas. Non-monoatomic gas. If I am talking about non-monoatomic gas, if I am trying to find out that what will be the change in Cp and Cv, then what do I feel that with the increase in temperature, if this is temperature axis, with the increase in temperature, both the values are of Cp and Cv increase, and this is that delta T. This is that, no. Cp and Cv both are increasing. This much you understand. And the difference between this Cp and Cv is called delta R. At any instant, there will be some difference between Cp and Cv, right? Why? Because Cp is higher than Cp. So this difference is called not delta R. This is R only, right? Like characteristic gas constant we have seen, and we have seen universal. So this is characteristic gas constant. So can I see that Cp minus Cv, this is equal to R, and this ratio Cp upon Cv is called gamma. And one more thing, that for non-monoatomic gases with the increase in temperature, both the values of Cp and Cv increase. Then what about gamma? This R value, this remains kya? Constant. This will always remain constant. But what about gamma? With the increase in Cp and with the increase in Cv also, like Cp and Cv both are increasing, but this whole value gets decreased. Okay. Now let us move to monoatomic gases. Monoatomic gases, what are the example? Inert gases like helium, neon, argon, these are nothing but monoatomic gases. So here your Cp and Cv, you have already seen that I have drawn the variation in a manner that Cp and Cv, this is always constant with respect to temperature. Like with the change in temperature, Cp and Cv value is not going to change, but this R value, the difference between Cp and Cv, gets changed. Okay. This is temperature axis. Okay. Okay. Let us try to find out Cp and Cv in terms of gamma. See, Cp minus Cv is equal to R, we have seen. Let us try to find out Cp or Cv in terms of gamma and R. So let me divide it by Cp, and Cv upon Cp is equal to R upon Cp. So this is Cp gone 1 minus this is what? Gamma. Cv upon Cp is 1 upon gamma is equal to R upon Cp. So when you expand this one, then this Cp value, can you feel that this is gamma minus 1 upon gamma is equal to R upon Cp. So Cp becomes gamma times R upon gamma minus 1. And what about Cv? So what you will do, that you will divide it by Cv. So Cp upon Cv minus 1 is R upon Cv. So Cv, this is gamma. So Cv is nothing but R upon gamma minus 1. We should know these equations also. Okay. Now, let us understand one very important phenomenon. See, we what do have in general for any substance? For any substance, we have the substance has some molecular activity, right? And this substance can have some molecular structure. Okay. And this substance can have some molecular mass also. Okay, so let me help you to know that specific energy, which we have just now talked, that specific energy will be dependent upon whom? Will be dependent upon, out of these three given, what we feel that upon which this specific energy will depend. So can I feel that this will certainly depend upon, this will certainly depend upon molecular structure and molecular mass. Why not on molecular activity? See, this specific energy, this is not specific, not energy, specific heat I am talking about. That specific heat will be dependent upon whom? Uh, See, we can have molecular activity, structure and mass. So molecular activity means what? That with the change in temperature, your activity is getting changed. But specific heat value, it is the amount of heat required which will be able to change the temperature of given substance, which is 1 kilogram by 1 Kelvin. Got the idea that specific heat is the amount of heat required to change the temperature of 1 kg substance by 1 Kelvin. Then this value is anyway will be remaining constant. This is never dependent upon that what is your molecular activity, means that it doesn't depend that if you are at 10 degrees Celsius, 1000 degrees Celsius or whatever. If the amount of heat required to change your temperature is, let us say that 4 kilojoule, then it doesn't matter that what is your molecular activity level, it will always require 4 kilojoule. Okay, so this will be dependent upon what? Structure and molecular mass only. Okay, so will be dependent upon molecular structure, and obviously we understand this, that molecular structure and mass will determine that what is the specific heat. And then what about internal energy? What about internal energy? Internal energy will be dependent upon these three. Why? Because we have seen that this energy was component of sensible, latent, chemical, nuclear and other things, right? So molecular activity is, and molecular activity is part of sensible, right? And latent, chemical and nuclear are dependent upon molecular structure. Molecular mass will also contribute into what? Sensible part. So I can directly feel that internal energy E will be dependent upon all three, like molecular activity, molecular structure and molecular mass as well. Why? Because we have seen that this energy has several constituents and these three are definitely representing any one of those. Okay. Okay. So let us now quickly move to first law of thermodynamics. Like till this point, we know what is system surrounding, we know what are the process, we know work interaction, we know heat interaction, we know ideal gas equation, we know how to apply it, we know the process, we know the amount of work required in various process. So after this, we need to find out the relation between heat and work interaction. So this is first law of thermodynamics which helped us. So let us understand first law of thermodynamics. So first law of thermodynamics is nothing but the conservation of energy, and this is also called Joule's law or conservation of energy. Okay, law of conservation of energy. So this is also called Joule's law. So what this law states that cyclic integral of heat into a cycle will be equal to the cyclic integral of work. See, if I am writing down the cyclic integral, cycle is nothing but, let us say that you have started your process from this one, then if you started process from this one and then you reached back to this one again, then this is nothing but a cycle. Like let us say this is 1 2 3 4. Then if you have started your journey from 1 and you reach back again to 1, then you name it as this is a cycle. Then first law of thermodynamics tells you that net heat interaction in a cycle will be equal to what? Net work interaction in that particular cycle. So if I generalize this first law statement, then I can write down that for a closed system undergoing a cycle, the net heat transfer is equal to what? Net work transfer. Okay. Now, since this q w is path function, then this q will automatically again become path function only. So can I write down few things about it? And there is one more interesting phenomenon, like when this is applicable when we are talking about a cycle, applicable to a cycle, applicable to the cycle, right? And when we apply this law to a process, then what did we found out? That this q, this q is equal to, now I'm writing down if it for the process, this is not valid for the cycle. Like, yeah, this is valid for the cycle also. This dE anyway will be 0. Why? Because the cyclic integral of property is always 0. Cyclic integral of the property is always 0. Okay. So this can be applied to the cycle as well. Why? Because this dE will become 0. Then I can say that del Q is equal to del W. Okay. So can you see from the first law few things? First thing is that heat is a path function. Heat is path function, one. And then we find out that energy is a property. Why? Because if you take the cyclic integral, then the sum of all the delta q's in the four process, like see, this is applicable for a process. Let us say that you are going through four process, like let us say that you are going to 1 2 3 4 these processes. Then you will apply this particular equation to what? 1 to 2, 2 to 3, 3 to 4 and 4 to 1. Then what happens that cyclic integral of del q will become equal to del w, then this dE is equal to 0. That is how you deduce that energy is a property. Why? Because the cyclic integral of E becomes 0, and we know that cyclic integral of a property is 0. Then this is how we reversed our analysis and we found out that energy is a property. Okay. And heat is path function we knew. Okay. Now let us understand the sign convention, because we have seen heat interaction, we have seen work interaction, and then we should know the sign convention as well. Like now when you will apply this first law of thermodynamics to any, let us say any system, then they will tell you that heat is coming in, heat is going out and all. Then what will happen, that you should know that how to treat the coming heat, whether it is positive, negative. Why? Because when you are putting it into a equation, you should be aware of the mathematical sign also. So we should what, before jumping to the question, we should prior develop a sign convention. So let me tell you what is that sign convention, which is usually followed. Otherwise, if you wish, you can follow your own sign convention. This will never change your result. So sign convention says that if heat is added to the system, heat is added to the system, if heat is added to the system, then we name it as, we treat it as positive. And if heat is rejected from the system, it is treated as what? Negative. Okay. And if heat, this is all about heat. Now let us talk about work. If work is added to the system, if work is added to the system, this is treated as negative, opposite to this one. Please mind these things. And if work is what? Rejected from the system, or work is output from the system, or work is taken out from the system. Better word is work is taken out from the system, then we name it as positive work. So now we are aware with sign conventions also. Okay. Now let us try to apply the first law of thermodynamics to various situations. See. So this equation, this we have seen that this delta Q is equal to dE plus delta W. So this E is constituting home internal energy plus kinetic energy and potential energy. This we know, but most of the time your change in kinetic energy. Why? Because if you are dealing with D, then you will deal with du, d of kinetic and potential energy. Then most of the time your change in kinetic and potential energies are negligible. Then can I write down this delta Q directly is equal to du plus delta W. Okay, this is very important equation we all should know. Okay, delta Q is du plus delta W. So let us now quickly we see. Now we know what is delta Q, delta W. We can find du based upon the what is the process. Why? Because delta W we know, delta Q we can find out for, let us say, constant pressure process, constant volume process. We can identify if it is isothermal, this will be directly zero. Why? Because delta T is zero. And no, let us talk about it rather than we talk. Let us talk in detail. Okay. So first thing is constant volume process. So I am talking about heat transfer in various process. Heat transfer in various process. So this will always be valid. What? This delta Q is du plus delta W. Okay. So can I write down this delta Q is du plus delta W? And more specifically, if I am applying this for closed system or control mass system, for closed system, we know that this delta W is PdV. So can I write down this delta Q is equal to du plus integration PdV? And now let us apply it to what? Constant volume process. Constant volume process. Okay, so for constant volume process we know that this value is 0. So can I write down this delta Q is directly equal to du, and delta Q at constant volume we know that this is mcv dt is equal to du. And can we see that whenever we are talking about constant volume process, we can find out what is the change in internal energy, and this is equal to mcv tt. And there is one experiment of Joule who proved that the internal energy of ideal gas is function of temperature only. Then your value mcv dt is equal to du. For ideal gas, it will be valid for any process. For ideal gas, any process. Okay. Okay, so Joule find out that for ideal gas, the internal energy is function of temperature only. Then you can apply this equation du is equal to mcb dt for any process. But let us say that you are talking about any general substance. Then du is equal to mcb dt is valid only when you are what? Dealing with constant volume process. Okay, get that. Then let us quickly talk about constant pressure process and then we will stop. So constant pressure process. What happens in constant pressure process? Let us again write down this equation. So this we know that delta Q is du plus delta W, and delta Q for constant pressure process we know that this is mcp dt, right? And du anyway we need to find out, and this delta W we know that this is p dv, right? And if pressure is constant, I can write down this as p into v2 minus v1. If you put this equation into the given one, then you will appreciate that du mcp dt is equal to du is u2 minus u1, and this is p into v2 minus v1. So there is one property called enthalpy, which is sum of internal energy and pv. This is called flow energy. So can you see that this is nothing but that u2 plus p2 v2 minus u1 plus minus of u1 p1 v1. So can I write down this one directly as H2 minus H1? So we are able to appreciate this fact also, that heat applied at constant pressure process is nothing but the change in enthalpy. Okay, but when this process is valid, if it is an constant pressure process and you have been asked that what is the change in Q, so this delta Q is H2 minus H1 valid for what? Constant pressure process. But again, Joule proved that for ideal gases, this enthalpy is function of temperature only. Then this Q is H2 minus H1. This can be applied for what? Any process. Okay. So this is about heat interaction in various process. Again, what process we are left with is third one is isothermal process, right? And what will happen for isothermal process? For isothermal process, we know that delta Q is du plus delta W. And then you need to find out, like for isothermal, you should know the magnitudes of du and delta W. Okay. So if it is an ideal gas, then can I write down this delta Q is du is nothing but for ideal gas, I can write down du as mcv dt and delta W plus delta W. See, if this dt value is 0 directly, why? Because this is isothermal, then this whole term is gone. So can I write down this one as delta Q is delta W, delta 2 Q is delta W. So this is one of the condition for what? Isothermal process and heat interaction. And for adiabatic process, Q will be anyway 0 only, right? Why? Because we told you now that for adiabatic process Q is always 0. Then what is the need to determine it? It will be automatically 0 only. Okay. So this is where we will stop, and then we will start from this point onwards in the next class. And then we will solve the questions based on first law closed system. Okay. Okay, so we'll stop here and we will continue in the next class.